Hello! In this video we are going to go over halogenation of alkynes as well as ozonolysis of alkynes. So let's start by reviewing what we know about halogenation with alkenes, and I'm going to draw a transalkene here, and we're going to add Br2 across the double bond. You could also use Cl2 here. You can't use fluorine because it's too reactive, and iodine won't work because it's not reactive enough. Now, what would our product look like? Well, would the bromines add on the same side or opposite sides of the double bond? So would we have syn addition or anti-addition of the bromine atoms? Anti-addition. Remember, we get that intermediate for this one. Okay, so if these add opposite each other, one way that we can draw that, we could show one bromine adding in a wedge position and one adding in a dashed position. And you could have flipped those two. The top one could have been a dash as long as the other one was a wedge. Now, let's rotate the left carbon that's bonded to bromine, because I want to show you what the stereochemistry looks like. So we have our bromine on the left is still a wedge, and then the bromine that's in a dashed position, when it gets flipped up, it turns into a wedge. Okay, so what kind of compound do we have here? Is this chiral or achiral? So there is a plane of symmetry. So this would be achiral, and it's a meso compound. I know meso compounds were a while ago, but they come back. They never go away. Okay, so this is also a dihalide. Now, would this be a geminal dihalide or a vicinal dihalide? A vicinal dihalide, because the halogens are on adjacent carbons. Okay, so that was just a bit of review on halogenation of alkenes, but what about alkynes? So let's just draw a terminal alkyne, and we're going to add Br2 to this alkyne. And we do need one more reagent to help us along, and that is carbon tetrachloride. Now, unfortunately, the mechanism for this reaction isn't well understood, so I can't really tell you how this occurs, but what essentially happens is the bromine atoms can either add opposite each other, or they could add to the same side. So you get both anti and syn addition on the triple bond. So we're going to end up with two products here. Let's see. So we'll show the opposite, or the anti-addition first, and then we'll show the syn addition. Okay, now the other way that we can refer to these double bonds is with E and Z. So remember, E means opposite, Z means same, because Z stands for zusammen, which has the word same in it. All right, so we have the E alkene on the left and the Z alkene on the right. Now, which one do you think is the major product? So both double bonds are equally substituted, so we can't think about that as one of our factors. But what else could what other theories do we know? What about electronically? Which one would be major and which one would be minor? So if we think about the electron groups surrounding the double bond. So really the only difference here is that on the left alkene, the bromines are really far apart. But on the right-hand alkene, they're closer together. Now, think about bromine's size. It has a lot of electrons, right? So if those bromine atoms are large and have a lot of electrons, do they want to be close together or far apart? Far apart, because remember, in theories like VSEPR theory, electron groups want to be as far apart from each other as possible. So the E alkene will be our major product. The Z alkene will be the minor product. Now, regardless of all that, if we add more bromine, so if we add another equivalent of Br2, we can perform halogenation of an alkene, similar to what we did up above. Now, if we do that, we're just going to end up with the same product, no matter if it's the E alkene that we're adding to or the Z alkene, because we're going to add a bromine on the left-hand carbon and the right-hand carbon, and the double bond turns into a single bond. So we'll have 2 bromines on the left-hand carbon, and then we'll also have 2 bromines on the right-hand carbon, although my pen decided to draw them in bold for some reason. I feel like the bottom of my iPad screen needs to be cleaned or something. Okay, so what we have here is a tetrahalide. So we have 4 halogens bonded to this molecule. Now, we don't have to worry about stereochemistry here because we don't have any stereocenters. None of the carbons are bonded to 4 different groups, so that's kind of nice. We don't have to worry about that. Now, you don't have to necessarily draw those intermediates, the alkene intermediates. You could just show that you can go directly from a triple bond to the tetrahalide using excess Br2 and carbon tetrachloride. Now, it is possible to just add one equivalent of Br2, or one molecule, essentially. So you could end up with the alkenes, but it kind of depends on the case, so I tend to just go all the way to the tetrahalide. All right, so that's about it for halogenation. Let's move on to ozonolysis of alkynes. So remember when we were performing ozonolysis of alkenes, what we basically did was we cut the double bond in half, and then we added an oxygen to each of those split double bonds. And your textbook, I believe, does show a better, more detailed explanation for that. But for our purposes, don't worry about it too much. Okay, so then we're just going to add an oxygen to the end of each of those split double bonds. So that gives us 2 products. Now, what's the relationship between those 2 products? Are they constitutional isomers, enantiomers, diastereomers, or identical? They're identical. And again, you'll notice that our alkene was symmetrical, so we should expect identical products. So just one product. Now, another question. Are these 2 products or one product? Is it a ketone or an aldehyde? So in this case, we formed aldehydes, but it is possible to form a ketone depending on what your starting material is. So you could form either ketones or aldehydes. Okay, so what happens if we do the same reaction to an alkyne? So let's just use our handy dandy terminal alkyne here. All right, and then we're going to perform ozonolysis. Now you'll notice that instead of DMS or zinc as my reducing agent, I used water. So when we're performing ozonolysis with an alkyne, we actually don't need a strong reducing agent. So we can just use water, which is readily available and greener to use. So let's just make a note of that. So we don't need a strong reducing agent. Now we're still going to split the triple bond in half, essentially. And what we end up forming is a carboxylic acid and carbon dioxide. So let's highlight our 2 carbons here. I'm going to highlight the left carbon in green and then the right carbon in purple. Okay, so the left-hand carbon forms the carboxylic acid because it's more substituted. And then the less substituted carbon forms carbon dioxide. Okay, so the green carbon, which was the more substituted carbon, again, that's forming a carboxylic acid. And then the purple carbon, which was the less substituted carbon, is forming carbon dioxide. So notice that with the triple bond, instead of adding just 1 oxygen, we're actually adding 2 oxygens to each of those carbons. Now, this is a terminal alkyne, so what if we had an internal alkyne? What would we produce? So let's see what happens. Okay, so let's draw an internal alkyne. And I'm going to draw an asymmetrical one just to kind of make it a little more challenging. Okay, so this is our asymmetrical internal alkyne. And we're going to perform ozonolysis. Okay, so let's see what happens. I'm going to still highlight my carbons just to keep track of what's going on. So we're actually going to form two carboxylic acids. So let's show the first carboxylic acid, our green carbon. So we're going to show that we end up with a carboxylic acid group, and then there's a methyl group off to the side. All right, and then let's look at the purple carbon. That is also going to form a carboxylic acid, and we'll have a, oops, what did I do? I don't know what happened. Okay, so then the group off to the side stays the same, so we'll just redraw that. All right, so we've got two carboxylic acids. Easy peasy. All right, so if you have an internal alkyne, that's going to give two carboxylic acids. But if you have a terminal alkyne, like we saw on the last slide, that actually will give you a carboxylic acid and carbon dioxide. Okay. So let's do a challenge problem. So starting with an alcohol, that has 5 carbons or fewer, make the following product. Okay, so we're going to try to figure out a synthesis problem here, kind of similar to the pods that you did last week. So if you want to try this on your own first, feel free to use any reaction that we've talked about so far. So substitution, elimination, addition, and you could use addition across a double bond or a triple bond. Now, I'll give you a hint. Because we just talked about ozonolysis, you can probably guess what we need to make this product here. But then you have to try to kind of make your way backwards to an alcohol as your starting material. So again, if you want to try this first, feel free to pause the video. And when you unpause, we'll go over it together. All right, so let's see how we can make this set of products. Okay, so we just talked about ozonolysis, and we saw that we produce a carboxylic acid and carbon dioxide, as long as we have a terminal alkyne, right? So let's work backwards here. Now, the carbon that ends up in carbon dioxide was originally on the end of an alkyne. The carbon that's in the carboxylic acid functional group, the green one that I highlighted, that one was originally bonded to the purple carbon. So it was the more substituted carbon in the triple bond. So we're just kind of working backwards here. So I'm going to draw that green carbon bonded to the purple carbon. Okay. So my green carbon is now bonded to the purple carbon. And I know that that was a triple bond. Is that the correct angle for a triple bond? No, I drew that wrong. So let's redraw it. It's okay to make mistakes. So remember, triple bonds are linear. So let's redraw that. Okay. So that's probably what we started with to get these products. And what would the reagents be? How do we perform ozonolysis on that alkyne? So we just saw that we need ozone, O3, and H2O as our reducing agent. Okay, so now we have to try to get our way back to an alcohol, because this is not an alcohol. So how can we form a triple bond? So how do we prepare an alkyne? So way back at the beginning of this chapter, we talked about vicinal dihalides and geminal dihalides, and that's what we would use to make a triple bond. We would also need a really strong base, right, to perform elimination. So I'm just going to draw a vicinal dihalide. Okay, so now I need to draw write my reagents to get from my vicinal dihalide to my alkyne. So again, we need a strong base, and we'll probably need an excess amount. So I'm just going to write XS for excess. Oops. And then sodium amide is the one we typically use to prepare alkynes. And then we also use water. Okay. Okay, so how do we make a vicinal dihalide? So kind of working back again, because this is not an alcohol, so we still need some work to do. So we just saw, actually, a couple slides ago, how to make a vicinal dihalide from an alkene, right? So we would need an alkene, and what reagents would we use to go from an alkene to a vicinal dihalide? Just Br2. It's just halogenation. Okay. I think we're getting closer here. So now, how can we make an alkene? Is there any sort of elimination reaction we could perform to make our alkene? And is there any way that we could go from an alcohol to an alkene? Yes. So remember, a long time ago we talked about elimination reactions involving alcohols. So there's a couple of different alcohols that you could start with. One of them that has 5 carbons has the OH group on the very end. And all we would need to add here is catalytic acid and heat. Now, you could actually also perform this in a second way. You could add tosyl chloride followed by sodium hydride. Oh, and you also need pyridine with the tosyl chloride. So this is from last quarter, right? So this is from our elimination reactions section of the textbook. Now, I mentioned that there's a second starting reagent you could have used. The OH group could have been on the second carbon in the chain. So don't forget those elimination reactions. In fact, I encourage you to make flashcards for substitution and elimination reactions as well, so that you can kind of mix them in with your addition reactions, because they are useful. We are going to use elimination reactions and maybe a little bit of substitution moving forward. Now, one more thing I just wanted to add to this problem. If you're having trouble keeping track of the carbons in your molecules, definitely number them. So for instance, I would have numbered the carboxylic acid 1, 2, 3, 4, and then the carbon in carbon dioxide as 5. So then I can double check that I still have 5 carbons in my product there, or starting material, I guess, since we're going backwards. And then I can just keep doing that as I go from step to step, just to make sure that I still have all of my carbons, because it is really easy to lose a carbon along the way. I see that a lot. So you just want to make sure you still have the right amount of atoms, because remember, we don't create atoms or destroy atoms randomly. Okay, so we'll stop there for this video. I believe there's only one more video that we need to do, and that's going to go over alkylation of alkynes. So we're just adding alkyl groups to an alkyne. And then we'll go over a summary of all of the reactions we've talked about in this chapter. So I'll see you in that video.